lecture, I will explain the all-day efficiency of a transformer. In what is the difference between the normal efficiency or commercial efficiency or power efficiency versus all-day efficiency. So the power transformers are fully loaded throughout 24 hours. The power transformers are loaded throughout 24 hours. But coming to the distribution transformer, and that is serves for commercial loads, commercial and residential loads. The input is 24 hours, but the output is not continuous. It is a hour basis. So go to the commercials, and morning 11 to night 9 o'clock it is fully loaded. The average load is only 30 to 40% of the full load. The average load of distribution transformer, so distribution transformer is 30 to 40% of the full load, and we can calculate the efficiency, that is all day efficiency, is output energy in kilowatt hour divided by input energy in kilowatt hour or output energy in kilowatt hour plus iron losses in kilowatt hour plus copper losses in kilowatt hour multiplied with 100. So hour basis means power multiplied with hour. We know that power multiplied with time, that is called the energy. So this is about the all day efficiency. And a normal efficiency or power efficiency is output power in kilowatts divided by output power plus losses in kilowatts. So this is the difference between the power efficiency and all day efficiency. Coming to the one problem, a 400 kVA distribution transformer has full load iron loss of 2.5 kilowatts. The iron losses takes place throughout 24 hours because the power supply is available or input supply is available for the distribution transformer, and the copper losses are 3.5 kilowatts. The copper losses will be varies with the load because the copper loss is directly proportional to I square, and during day its load cycle for 24 hours is 6 hours 300 kilowatts at 0.8 power factor and 10 hours 200 kilowatts at 0.1 power factor is given. Determine its all day efficiency. So the S value is 400 kVA. S value is 400 kVA. Iron loss is 2500 watts, 2.5 kilowatts, and the copper loss, so that copper loss is WCU, that is called the full load copper loss, is equal to 3.5 kilowatts, that means 3500 kilowatts. So iron losses are takes place throughout 24 hours. Iron losses in 24 hours is equal to 2500 into 24. So 2500 into 24. So 2500 into 24, that should be equal to 60,000, means 60 kilowatt hour. And coming to the first load, 6 hours 300 kilowatts at 0.8 power factor. So now you can calculate kVA for 6 hours. So 300 kilowatts. So kVA is equal to power divided by cos phi, P1 divided by cos phi. 300 into 10 to the power of 3 the power factor value is given as 0.8. divided by 0.8, that should be equal to 375 kVA. So we can find out the fraction. The overall kVA is 400 kVA. Now find out the fraction. Divided by 400, that should be equal to x is equal to 375 divided by 400 kVA, 0.9375. So why I am calculating means the kVA utilized by the transformer during the first section is only 6 hours, and that too 300 kilowatts is utilized at 0.8 power factor. Overall 400 kVA is not utilized by the load. It's a, there is a some fraction is there. X is equal to 375 by 400, that should be equal to 0.9375. The copper losses at this moment x square times of I2 square R naught 2, that is x square times of full load copper losses into 3500. So into 3500, this is 0.9375 whole square into 3500 is equal to 3.076 kilowatts, and this is called the copper losses 1, WCU1, and this kVA for 6 hours, and the copper loss 1 at 6 hours. You can find out the energy. So energy is wasted or heat is produced 3.3076 into how many hours? 6 hours. Then 3.076 into 6 hours, 18.457 kilowatt hour. So this is the first one. And the second case, 10 hours 200 kilowatts, 10 hours 200 kilowatts at 0.7 power factor. Then S2 you can calculate 200 into 10 to the power of 3 divided by 0.7. 0.7, that should be equal to 285.71 kVA. Now find out the x2 value, that is a fraction value, divided by 400, 0.7142, that is 285.71 divided by 400. Then copper loss 2, that is WCE2 is equal to x2 square times of full load copper loss. So square into full load copper loss is 3500, 0.7142 whole square into 3500. Then I got it as 17.85, remains 1785.7, that means 1.785 kilowatts. This is for 10 hours. Then copper losses in kilowatt hour. So during 10 hours, multiply with 10, then you will get 17.857 kilowatts. And the third one, coming to the third case, 4 hours 100 kilowatts at 0.9 power factor. 4 hours 100 kilowatts, 0.9 power factor. Find out the S3 value. 100 into 10 to the power of 3 divided by 0.9. 100 divided by 0.9 is equal to 111.11 kVA. X is equal to 0.2777. That means this is x3 111.11 divided by 400 kVA. So x3 square into full load copper loss. The full load copper losses into full load copper losses is 3500. 0.277 whole square into 3500, that should be equal to 270.06 watts, and this can be used 4 hours. So copper loss 3 in 4 hours so 1.080 kilowatt hour. And coming to the fourth one, 4 hours at no load. 4 hours at no load means the secondary current is 0 and the copper losses in this section is 0. Now the total copper loss in kilowatt hour, that should be equal to copper loss 1 in kilowatt hour plus copper loss 2 in kilowatt hour plus copper loss 3 in kilowatt hour. The copper loss one is 18.457 plus 17.857. The copper loss in 4 hours is 1.080 kilowatt hour. Plus 18.457 plus 17.857. So total copper losses in a kilowatt hour is 37.394 kilowatt hour. Yes, the output power is given in 24 hours, right? So all day efficiency is total output in 24 hours divided by total output in 24 hours plus iron losses in 24 hours plus copper losses in kilowatt hour. So because the copper losses are not taking place in 24 hours, first of all you should calculate total output energy in a day, that is 24 hours. So this is called the energy output. Energy output is given as 300 kilowatts in 6 hours, 200 kilowatts in 10 hours and 100 kilowatts in 4 hours. So multiply with that means 300 into 6 hours plus 200 into 10 hours plus 100 into 4 hours. 6 plus 10, 16 plus 4, 20 hours only, and the remaining 4 hours the output power is 0. The remaining 4 hours output power is 0. Why? Because it is operating under no load conditions. So 4200 kilowatt hour, and substitute here in an all day efficiency 4200 divided by 4200 plus 60 plus the 60 is the iron losses in 24 hours. The iron losses in 24 hours is how much? 60 kilowatt hours, and the copper losses in overall copper losses we are getting 37.394. 37.394 multiplied with 100, then I got it as 97.73 percentage. That is the all-day efficiency of transformer. Coming to the next problem. A single phase transformer has its maximum efficiency of 98% at 15 kVA at unity power factor during the day. So that means during the day means 24 hours. It is loaded as 12 hours 22 kilowatts at a power factor of 0.5 and 6 hours 12 kilowatts at power factor of 0.8, 6 hours 18 kilowatts at power factor of 0.8. Find the all day efficiency. Find all day efficiency. So efficiency is 98% at 15 kVA. So efficiency formula that should be equal to, so what is the efficiency is equal to output power divided by input power. So from this we can calculate the input power is equal to output power divided by efficiency, that is called the maximum efficiency is given. So 15 kVA divided by 0.98, that should be equal to 15 divided by 0.98, 15 divided by 0.98, I am typing in calci, that is 15.306 kilowatts. 15 kVA at unity power factor. Yes, the power factor is given as 1. So kVA into cos phi, that should be equal to active power. So after that, input power minus output power will use the total losses. So now the total losses is equal to, so 15.306 minus 15, that should be equal to 0.306 kilowatts. And finally I got it as 306 watts. At the maximum efficiency, iron losses and copper losses both are same, and now the total losses 2 times of iron losses is equal to 306. From this, iron losses is equal to 306 divided by 2, that should be equal to 153 watts, and the copper loss is also 153 watts. So coming to our all day efficiency, 12 hours 2 kilowatts at power factor of 0.5, 12 hours 2 kilowatts at power factor is 0.5. So S1 you can calculate 2 divided by 0.5, that should be equal to 4 kVA. Then find the x1 value, that is a fraction value, 4 divided by 15. So copper loss 1 in kilowatt hour, the copper loss 1 is kilowatt hour, x square times of full load copper losses, x square times of full load copper loss. So this is WCU or PCU. So 4 by 15 whole square into 153, so that should be equal to 10.88 watts. If you want to check it in calci, you can check it 4 square divided by 15 square into 153, it is 10.88 watts. Similarly, find out the second condition. In that second condition, you can see now 6 hours 12 kilowatts at power factor of 6 hours 12 kilowatts at the power factor of 0.8. Find out S2 value, 12 divided by 0.8. Then I will get it as 15 kVA, where x2 is a fraction. So 15 kVA means that is 15 divided by 15, that is under full load condition. The copper losses at full load is now 153 watts only. But this 10.88 copper loss in kilowatt hour is equal to 10.88 into how many hours is using in how many hours? It is 12 hours. So 10.88 into 12, that is 130.56 watt hour. Okay, 153 watts into this 153 into how many hours? That is 6 hours only. This is copper loss 2 at kilowatt hour or watt hour. 153 into 6 hours, that is 918 watt hour. So if you want to convert in kilowatt hours by 1000, you will get. And the third one is another 6 hours. 6 hours, 18 kilowatts. 18 kilowatts at 0.8 power factor, another 6 hours it is loaded. S3 is equal to 18 by 0.8, 22.5 kVA, and X3 is equal to 22.5 divided by 15, that is 1.5. So 1.5 whole square into copper loss is 153. That should be equal to WCE3. $344.25, and the copper loss in kilowatt hour into 6, 344.25 into 6, 2065.5 watts hour. Then the iron losses are taken place in 24 hours. Now the total copper loss in 24 hours is equal to, if you add all, so this is third, 2, and this one is 1. If you add all these three, then finally I got it as 3.11406 kilowatt hour. And the total iron loss in 24 hours, 153 into 24, so that should be equal to 3.762 kilowatt hour. Then output in 24 hours is 2 into 12 plus 6 into 12 plus 6 into 18, that should be equal to 204 kilowatt hour. Then input in 24 hours, output in 204 plus 3.11406 plus 3.672, finally I got theta as 210.7861 kilowatt hours. And the all day efficiency is equal to 204 divided by 210.7861 into 100, 96.78%. This is about the all day efficiency for this problem. Compared to the previous problem, here is given as indirectly, losses are not given, is indirectly given as a maximum efficiency. And from the maximum efficiency you can find out the input power, and after that losses you can calculate, and total losses you are obtaining total losses. From that you can calculate the iron loss and copper losses. Then you should find out all day efficiency.